We have a great afternoon session of speakers. First up is Bodhisattva Sen from Columbia, and he'll be speaking about adaptive inference with a multidimensional, multiscale statistic. Bodhi?
Thanks, Richard. I would like to thank the organizers for this kind invitation. It's a pleasure to be here. This is joint work with a second year PhD student at Columbia, Pratyay. And the first thing I should do is to first of all explain what the title says and the roadmap. But before I start, I want to just set a few ground rules. This is very much ongoing work. The papers are yet to be posted on archive. So please feel free to comment or ask questions, okay? If you have any questions, I'll be more than happy to stop and explain. So the roadmap would be to introduce the multiscale statistic. And as ours is a multidimensional multiscale statistic, I think it's best to first of all go back to the one-dimensional setup and look at this seminal paper, as far as I feel, by Duncan and Spokane, and then introduce the statistic, and then I'll talk about the optimality properties of the multidimensional analog of that, and then use this multiscale statistic to do confidence band for shape constraint estimation problems. Okay, so that's a goal. Again, please feel free to stop me if you have any questions. So what is the problem about? The problem is, you can think about it as a classical non-parametric regression problem. In a non-parametric regression problem, in the most simplest setting, you have an unknown function f that you want to estimate. Now yi is your observation, is your response, and suppose I am assuming an equidistant design point. So I over n is the xi's, and you assume a model like this. For simplicity, I'm going to even assume IID normal and variance to be 1. Okay. So that's really the where this sort of a problem can be useful. Non-parametric regression. I'm going to even make a simplification. I'm going to not work with this discrete model. I'm going to work with what is called the continuous analog of this model, which is sometimes called as the Gaussian continuous white noise model. So this is how the model is posited, and you can see that this is similar to this model if you just do this transformation. If you basically look at the partial sums, I is equal to 1 through j, and you do this for everything, this is basically like a Brownian motion, and that gives you the Wt, and that properly scaled is square root of n times f of x d of x, and this is my observation. So now I don't have any covariance to deal with. I have a stochastic process, yt, t belonging to 0, 1. Here n still represents the notion of a sample size, w is a Brownian motion, and the goal is to make inference about f, and I want to talk about optimal inference. So I should first of all try to talk about what kind of inference I'm interested in. Now a point that this is so it's not only it's not me who is doing the simplification for the first time. It's known under very broad scenarios that these two models are somewhat equivalent, or as they would be said properly, asymptotically equivalent, which means inference here can be translated to doing inference in this model. Okay. So what sort of inference problems am I interested in? The first part of the talk, where I'll talk about optimality, I'll talk about testing f is equal to 0 versus f non-zero but belonging to a Holder class of functions. So what is a Holder class of functions? H beta L. So a Holder class where beta is between 0 to 1 is basically, it's like Lipschitz, but it's a minus b to the power beta. The L is like the Lipschitz norm, and when beta is greater than 1, if it lies between k and k plus 1, then I'm assuming k times differentiable functions, and the k derivative satisfies these conditions. So this is the definition of a Holder class. I'd be interested in optimal testing in this situation. Another scenario I would be interested in is optimal testing for this sort of a problem, where you have a constant 0 versus, and there's a small jump of height mu n in a small interval in, and I want to devise tests that are optimal in some sense. Okay, so these are the two inference problems I'll be interested in first. Questions? So let me now go. So basically, as I said, I'm just motivating the multiscale statistic. I'm going to follow the paper by Duncan and Spokane. So this is the model they had. So what is multiscale? Multiscale to me is basically, the idea is kernel averaging. So I'm going to do basically construct kernel estimates of my underlying function. So what is a kernel? A kernel, as I define, is basically I'm assuming compact support between -1 to 1 function in L2 has finite total variation, and integral of f of psi of x dx is positive. So note, I'm not normalizing them immediately, but psi over this would have integral 1. I'm allowing it to be slightly more general. So psi is my kernel, and now I look at the kernel that is centered at t with bandwidth h. That's basically the centered kernel, I would say. And it's easy to show that this is the really the continuous analog of the kernel estimator that all of us study, like the Nadaraya-Watson estimator. You can think about this is the continuous analog of that. Okay, and inner product of 1 comma psi has this interpretation. Okay, so to fix your ideas, if you really have say the box kernel, as I call it, a kernel that is 1 in between -1 and 1, then this is exactly what f hat of h is. And so I want to motivate the multiscale statistics. So this is my kernel estimator using kernel psi at bandwidth h. And then I can use this kernel estimator to construct a test for ft equal to 0. Note that I really want to do a test for ft global equal to 0. And what do? I have this kernel estimator under the null hypothesis. I standardize it, and that will have a normal 0-1 distribution. And I can reject a test of ft equal to 0 if this is this exceeds a particular value in absolute value. Okay. So that's just an easy test that you can do. But note, we are interested in testing f is 0 everywhere. So we would like to do it for every t, and that is a test statistic that you might use. So marginally for every t and for every h, this is like a normal 0-1, but you want to test whether the function is 0 everywhere, so you take a supremum for t belonging to h to 1 minus h. Why do I leave out this endpoints? As I have said, my kernels take values in -1 to 1, and I do not want to deal with boundary effects, so I just restrict myself to t between h to 1 minus h. So this could be a test for the hypothesis f is equal to 0. Okay. Now a nuisance with this test is, of course, it depends on the bandwidth, but if the function is 0, then at every bandwidth the same intuition should hold. So you might look at this test, which is you soup out over all bandwidths. Okay. And this is my first multiscale statistic. By multiscale I mean you are looking at large bandwidths where h is close to half, on small bandwidths where h is close to 0. And the idea is that as we are looking over all the spectrum of large scales and small scales, hopefully you will be able to detect departures of both forms. Okay. So now to fix ideas, you can come back and you can say, okay, what is this really? In the discrete setup, which is what most real data would be like, you would have f equal to I over n, yi equal to f of xi, which is I over n plus epsilon I. Then what am I saying? And if you use the box kernel, I'm saying look at boxes of arbitrary lengths centered at arbitrary points. So you basically look at I and j between 1 through n, and you look at this normalized statistic, and you're looking a max over this. So this is the discrete version of this quantity. Any questions?
Yes.
Yes.
With the boundary effect, if the age is not fixed, then the range of the test is different, right?
Yes.
But
So
for each, I mean, if you're trying to find out the soup of the age, I mean, basically you get back to the boundary.
yeah, so I am leaving away the boundary. So for every fixed h, I am only going to look at h to 1 minus h.
But that's not correct. I have the feeling that the smallest age is the thing that you should look at, because if you take a large age, you would kind of average out everything.
So
If you take the smallest
so-
one, somehow you get back to the boundary, don't you?
okay, first of all, there are two things. I should look at big h's too, because if the function is say slightly non-zero but over a large interval, if I just take a small bandwidth, it will not be able to detect this. So I need to take an average over a large interval, and that's why I do that. Okay, and as I said, the boundary issue will not really cause us any trouble. But yeah, I don't want to use a boundary corrected kernel and something, so I just leave that.
Maybe I ask you, I'm wondering why second soup depends on age, because your interval becomes
Okay.
very small or large. That is
No, so because you see, my kernel is between -1 to 1, and if I take a value close to 0, then I have to average observations beyond 0, and I don't want to do that. Okay, so this is what is called a scan statistic in one dimension, and to detect departures from 0, a lot of people look into this statistic. And the obvious advantages is that, of course, it bypasses the choice of any bandwidth, and of course this looks at all scales, which is probably important. But in my continuous setting, it's good to propose this statistic, but it's going to be plus infinity almost surely. And so we cannot just use this statistic. And why is it going to be plus infinity? It's actually easy to see. So under the null hypothesis, now take a bandwidth of 1 over 2m, where m is an integer. So then I can chop it off, this entire from with this supremum is of course greater than or equal to supremum for this discrete t's, and as I center the t's at this I over 2m plus 1, and I have a bandwidth of 1 over m, I'm getting independent normals, and I have m many of them. I'm looking at the absolute values of m many independent normals, and that is already of order square root 2 log m. So if I allow this supremum, this is, and if I allow m to be really large, this is going to blow off to infinity. Okay, so the first motivation is that this statistic as it is proposed is not probably the right thing to do. There needs to be some adjustment to this to make it finite, and that's the first one. Okay, any questions? Okay, so now let's look at the multiscale statistic proposed by Dumgen and Spokane in their 2001 paper. What they did, they have this normalized statistic which marginally follows normal 0, 1, and they subtract of a term, they penalize a term which you can think of is like the mean at this bandwidth, and then they standardize by something like dividing by the standard deviation. But the d term will be less important to us. What is going to be most important to the talk is this subtraction, this penalization term. The term you can exactly penalize is square root 2 log 1 over r, which you already see coming up here. Because at small scales, what is going to happen? At small scales, you'll be looking at the maximum of many independent normals, and you have to do some sort of an adjustment to make this finite. Okay, so this is the multiscale statistic that was proposed, and this gamma is the most important function. Can be thought of as bringing all scales in the same footing, because if you don't do a normalization, the small scales dominate. The maximum is going to be attained for the small scales. And as you will see that this is really a multiple testing problem, right? We are doing so many multiple tests. At every t, we are looking at different bandwidths, and we are doing a multiple testing problem, and we have to resolve this multiple testing issue, and this is one way of resolving it through one statistic, which carefully penalizes every statistic carefully. Okay, so one of the main results in Dumgen and Spokane show that this statistic is actually finite almost surely, and so you can use the quantiles of this distribution to do a lot of inference, which is what we are going to deal with. Okay, so let's talk about inference now. So again, this is following the result that Dumgen and Spokane had in one dimension. So in one dimension, they wanted to test whether a function is 0 versus it's non-zero, and but it's in a holder class with beta and L as the parameters. And I'm going to use the multiscale statistic that they proposed. This is the multiscale statistic they proposed, and with a particular choice of psi, which is psi beta, which you can only know if beta is known. For beta between 0 and 1, it has this simple form. For beta beyond, it's a solution to an optimization problem, which I don't want to discuss here, but it can be computed. So this is a rate, and this is a constant. The product of these two will play the crucial role. So what does the first theorem say? The first theorem is like an impossibility result, which says, so to test this hypothesis, right? The first theorem says, so this is my detection threshold, C star times rho n explicitly mentioned. As soon as I allow for signals which have signal strength, which is an infinity norm of G, slightly less than this threshold, no test can have non-trivial power. That's what this says. So in FEMAM, so basically you give me any sequence of tests, level alpha tests, I can find a point in this space which is slightly below the threshold, such that for that particular point this test will fail to detect this. The optimality result says as soon as you go slightly beyond this threshold, so it's 1 plus epsilon n as opposed to 1 minus, and C star rho n is the detection threshold, then for every point in the alternative as n tends to infinity, the multiscale statistic will have power 1. Okay? So this is what I mean by optimality for testing against Wölderian signals. Does this make sense? Any questions here?
What happens at the boundary? If you just take C star rho n?
I don't know. I guess, yeah, I don't know. I think, I don't think you can have power 1 for the multiscale test at least. Okay, so now, so here a quick point is that beta needs to be known because you want to use a kernel which depends on beta. L need not be known. But if you don't want to assume anything on beta, you can construct, you can look at the triangular kernel, but then you won't get the exact constant. Then the rate would be the same. Rho n is the rate of detection and C star is the exact detection boundary. If you use a different kernel, the rho n would remain the same, but the constant would change. Okay? Yes?
Just a remark here that these results are not robust to you taking the L infinity norm here. I mean, if you take for separation, I mean, you're not the author of these papers, of course, but why would you consider the L infinity norm separation as natural in this setting? Why not L2? And actually, if you would do L2 separation, these tests would not be optimal any longer. So
okay.
I'm just trying to remark that this is
That's
not
a good point.
robust to
Okay.
how you actually think of separating hypotheses.
Okay, okay. Thanks.
Do you
Yeah.
have any justification or motivation for using L infinity norm?
No. I was just, I'm just trying to say what they did. And because we are trying to extend this sort of work. Yeah. So thanks, Richard. That's a good point. Okay. Now the other kind of signals that I want to detect is f is equal to 0 versus f, which is non-zero, has the value mu n at an interval in, where this interval in can be shrinking to 0 as n tends to infinity. So it's a 0 function. In a small region, it has the value mu n, and I want to detect this. Of course, I do not know mu n, neither do I know the interval in. And suppose, and this theorem has two parts, suppose if the signal is on large scales, which means basically the Lebesgue measure of this in is basically non-zero. So there's a non-trivial interval where this signal is basically there. Then the impossibility result says that this is like the signal strength. This is you just so if I were known, then you could have just taken an average of the y's and then gotten the best test, but the in is not known. But this is like the signal strength, and this impossibility result says if the signal strength is finite, then and if you have any function like this, then the power cannot be 1. And the optimality of the multiscale statistic says as soon as the signal strength, the way I define it, is infinite, then for every function in this alternative space, the multiscale statistic will have power exactly 1 in the limit. Okay, so this is optimality in large scales. Why large scales? Because I'm assuming INs are big in terms of Lebesgue measure. And again, this proof was not there in Dungan's paper, but Axel Monk and co-authors and Gunther Walther and others have also worked on this and have shown this for not only the multiscale statistic proposed here, but for some other kinds of statistics. Now, what happens when we take small scales? So in small scales, I'm assuming like the Lebesgue measure of in is going to 0. Again, I'm using the sort of the box kernel. And now the threshold, the detection threshold is basically, so this is like my signal strength, and this is what I get from you can think about, get from the maxima of normals. So they have to be equal, and that's the detection boundary. And this theorem says if this is less than or equal to 1 minus epsilon n, then again, for any test, there would be an element in the space which will have power less than or equal to alpha, which is a bad test. And the optimality result again says as soon as you take as soon as you increase just slightly above the detection threshold, the multiscale statistic will be able to get this. Okay. So now I must say that there are other competitors. You can look into just the scan statistic, the average likelihood ratio statistic. They don't have these optimality properties. At least it's only the multiscale statistic that I know of has this in both regimes, the small signals and the large scale signals. Okay, so this is just a recap of what is already known. What are we trying to do? We are trying to say how do we extend this beyond one dimension. So I want to now go beyond one dimension, so d is greater than or equal to 1. I'm going to consider again multivariate Gaussian white noise model, which has this formulation. So now this was the Brownian motion in one dimension, this becomes the Brownian sheet in d dimensions. The Brownian sheet, as you can see, is basically the extension. So in Brownian motion, you basically average terms all the way from 0 through t. Here you look at this hyper rectangle starting from 0 to t, and you average the errors, and you would get a Brownian sheet. And the goal is the same, to make inference about my function f, when the observations is just y. This is the y that is only given to me. Okay. So I repeat the same game. I define a kernel. What is a kernel? It has bounded support -1 to 1, is in L2, is of finite total variation. Now as soon as you go beyond one dimension, total variation is not a very easy concept, but there are many notions of variation. We use the Hardy cross variation, and then the same thing about integral psi of x dx greater than 0. So this is my kernel estimator now, and I can play the same game. I can define my normalized kernel estimator, which is this estimator divided by its variance. And if you want to test the hypothesis, for example, ft equal to 0 versus ft not equal to 0 for a fixed t, so oops, I'm sorry. All I would do is look at this normalized statistic and reject this if for large values of this. So it's everything is the same till now. Now I have to be a bit more precise. I wanted to avoid the boundary effect. So now for a fixed h, I can define this set AH, which is basically I leave out something close to 0, something close to 1, and I am in a smaller rectangle than 0, 1 to the power d. And you can, for every fixed t, you can look at the supremum of the statistic as t varies in that set, or if you want to use a multiscale approach which uses all bandwidths. Now by here I'm considering bandwidths that are products, that is h1 through ht, and it's not the same h, right, and that's important. Or you can consider something like the scan statistic, which looks over all bandwidths and all values of t in that region and looks at the supremum statistic. And then of course you can ask what happens to this statistic. No surprises, this is going to be plus infinity. So the question is, can we scale this properly so as to get a finite limit which can be used for detection, optimal detection. So here is our first result. We say that look, you use the exact same quantity as you did in one dimension. You have the normalized statistic, subtract off the same penalization, square root of 2 log 1 over r. There is no other constant here, and that's very important. I'll come to that. And then you basically get a statistic which is the exact analog of the one dimension case, and we are going to claim that this is going to be finite. And this again has the same intuition. You're looking at a lot of different scales, and it brings all the scales in the same footing, resolves the multiple testing issue. Okay. So let's now simplify, and let's try to see, okay, what does it mean in a simple problem. So when d is equal to 2, let's try to write out the discrete analog to this continuous model. So I have now design in ij, and so I'm in a regular uniform grid, and that's suppose my observations. If you use the box kernel, then the multiscale statistic reduces to this. So what am I doing? I'm looking at rectangles I1 J1, I2 J2, and I'm looking at the average, and I'm subtracting off some term, dividing by some term, and I'm looking over all rectangles. And that is my multiscale statistic. And of course, we would expect if there is signal, there has to be signal in some place, and this statistic will be large, and this statistic will be able to optimally reject it in those situations. One thing, of course, this is expensive to compute, as you can see, because I have to look over all rectangles. And there is quite a bit of work, especially by Gunther Walter and also Axel Monk and others, that have tried to say we don't need to look at all rectangles. We can maximize over a sub-collection of rectangles. And in fact, Walter in the d equal to 2 case proposes a scheme of choosing rectangles which will look at essentially of order of n many rectangles and have still all the optimality properties that this computationally expensive estimator might have. But I will not address the computational issues in this talk. Okay. So the first result of our paper shows that this multiscale statistic, so defined, is finite. Now this is where actually a lot of machinery goes. Means it's not, at least to me, it's not obvious to show that this is finite. And in fact, in a very recent paper by Axel Monk and his collaborators, they show that instead of by this gamma has no v. If you see, this gamma has no v, or the v is 1. If you replace the, if you introduce a v, you get a penalization term. And I think Axel Monk and his collaborators show that you can take v to be 2d minus 1 plus epsilon for any epsilon when d is greater than or equal to 1. But we say the v can be exactly chosen to be 1. And that obviously has repercussions in finding optimal tests. And of course, v cannot be less than 1, because if v were less than 1, this is obviously, this will, at small scales, this is like maximum of independent normals, and if v is less than 1, then this is infinite. So in some sense, we have the optimal penalization also, which leads us to optimal detection. Okay. So now let's go over the analogs of the one-dimensional theorems. It's very similar. I am now restricting beta between 0 to 2, Holder between 0 to 2, and I have a very similar looking rate where the 1 in the previous slide is now replaced by d. The constant C star looks very similar. The d's were 1 in the previous case. The impossibility result, first of all, says that so this is the product C star times rho n is the detection boundary. If you are slightly less than the detection boundary, that there will be a test such that whatever, there will be a g for whatever test you use cannot have power greater than alpha. And what we say is, if you are slightly above the detection boundary, 1 plus epsilon n, and the signal strength is bigger than this, in basically not the boundary. So basically, I restrict myself from going to 0 and 1. I slightly come from 0 and slightly less than 1, just because I'm not tackling the boundary issues very well. But this, of course, this interval as n goes large is converging to 0, 1 to the power d. So there is signal that is interior, and then if this exceeds the threshold, my multiscale statistic will detect it. Yes.
The impossibility result, you mean expected value under g of 1 minus phi n is less than alpha, or?
G of
1 minus phi n, I mean the type 2 error, so phi n is a test function that takes 0 to pick the null hypothesis.
Yes.
Should it be 1 minus there, or?
No, this will be alpha. So, oh yes, sorry, of course. Thank you. Okay. So now let's go on to optimality for constant signals. So now again, I have a signal which is mu n in a rectangle parallel to the coordinate axis, and bn is the strength of this, and bn is the size of the interval. The bn can shrink to 0. First of all, let's look at the large scale, where so we have a rectangle and there's a signal mu n, and the question is, can we detect this? As before, if the signal strength is finite, no test can have will have power 1. As soon as the signal strength is infinite, the multiscale test will have power 1. For small scales, now that's a typo, that should be bn. If you have a rectangle whose Lebesgue measure is going to 0, then you again have to exactly compare these two terms, the signal strength versus the term coming from the maximum of normals. And if you're slightly below the detection threshold, no test can succeed, whereas for us, the multiscale test, as soon as the signal strength is slightly above the detection threshold, we succeed. And again, I must say that there is really no constant. This is just in that sense sharp, because there is up to constants we are sharp. Okay. So the first part of the talk ends here, where we have proposed a multidimensional multiscale statistic, show that it's finite almost shearly, and illustrated its optimality in testing f equal to 0 versus Holderian alternatives and for constant signals. And as I said, there is a scan statistic, average likelihood ratio statistic, and so on. Unless you are careful with them, so that there is the average likelihood ratio is not optimal, but you can drop away some terms, not take averages over those, and then you can make it optimal. But this seems to be a more neater way of proposing a optimal test. Okay. Yes.
But the lower bounds, I mean, they're not new. I mean, Inkster proved them in the 90s or something.
Yes. Thank you. So adaptive, so now let's move on to the next part of the talk, which is adaptive confidence bands in shape restricted regression. So again, I'm going to confine myself to this white noise model, and I'm looking at a class of functions f which belongs to script f, where f is shape constrained. So the two prime examples, it's multivariate isotonic or multivariate convex. What is multivariate isotonic? That means I have a function so that u and v are coordinates, so that if every coordinate of u is less than or equal to the corresponding coordinates of v, then the function value at u must be less than or equal to the function value at v. That's what multivariate isotonic means. And for multivariate convex, it's just this illustration, just an extension of what convexity means. So these are my two prime examples. I want to construct confidence bands for them. Okay. So I want to construct confidence bands. So what do I mean? I want to find L hat and U hat which satisfy this, which have guaranteed finite sample properties. So which is greater than or equal to 1 minus alpha for all n for all elements in this function class. Okay. And I want to have basically a band which has smallest width, which is U hat minus L hat must be small for an in an appropriate subset of 0, 1 to the power t. So these are the two goals. I want to construct a confidence band that has guaranteed coverage with smallest width as much as possible. So here are a summary of our results. So we will show that at the optimal bands that we get from using the multiscale statistic adapts to unknown smoothness and the intrinsic dimension of the function class, and in some cases, in some special cases, it also has the smallest possible width. And this extends a work by Dumgen in 2003, which considered d equal to 1 in various ways. So let's see how we would do this. Again, this is the model. I am going to my approach is the same. Do kernel averaging. That's the kernel. That's the kernel centered at t with bandwidth h. This is the kernel density. This is the kernel estimator of f. You can just do simple calculation of what is the mean and variance, and this is the mean of the kernel estimate, and that's the variance. Now, the great thing that this multiscale statistic does is basically you can control this random fluctuation uniformly in t, uniformly in h. That is what the multiscale statistic does. So you look at this fluctuation, that's basically this, that simplifies to this quantity, just simple algebra. And this is exactly the normalized statistic that I looked in the previous slide, where the W is now Brownian sheet as opposed to Y. So the idea is that this is a normalized statistic, and I can control the random fluctuations of my kernel estimator over all bandwidths at every point, because this is finite. Okay. So that's the first part, and then in most cases, you see, as I said, the gamma is the most important part. This penalization is what is important. Dividing by the d is not that important. You can actually forget that, and this simplifies things quite a bit. So now you have t. By the previous work, I know that this statistic is actually finite, almost surely. So I can control the random fluctuations. To construct a confidence interval, I have to also deal with the bias term. Okay, and that is what I'm going to deal with next. So how do I deal with the bias? If I could deal with the bias, then I can use this to construct confidence bands. So now I have bypassed one crucial question. I've always said I want to do shape constrained inference. What is shape restricted? I have said there are two prime examples, convexity, monotonicity. But the real thing that I really need, and that is what defines shape constrained inference, is that in shape constrained inference or in shape constrained estimation, you can find kernels where the bias can be bounded, can be both lower bounded and upper bounded. So for example, this is similar. So why is the isotonic case shape constrained? Because suppose we want to understand the value of an isotonic function at a point t. If I look at all a rectangle, like, so if I have a kernel 0, 1 to the power d starting from t, and if you take an average of the kernel, the expectation value, just because of isotonicity, I know that this has to dominate f of t. And that is what I mean by shape constraint. Similarly, if I have -1, 0 to the power d, that's so basically I'm looking at this rectangle. I have this point t, I'm taking averages of this form. This of course will be an underestimator of the value of the function. If I take things like this, it's going to be an overestimate. So I have a way of bounding the bias which is not available if I did not have a shape constraint family. So that is important, because as I said, to construct a confidence band you need to tackle both issues, the random fluctuations and the bias. And in shape constraint you can do it. You automatically get a bound on the bias. And of course our multiscale statistic gives us a bound on the random fluctuations. So that's really at the heart of what's going on. Okay, any questions here? Yes.
Typically that bound will not be tight.
That's a good point. Yes, it will not necessarily be tight, and in some situations it will be tight. Yes, and that is why the rates we'll get are going to be different. Okay, so let's now see this. So now I have a class which is shape constrained. By that I mean you have such bounds for some kernels psi L and psi U. This is my multiscale statistic, which I know is finite. I want to say construct a lower bound for f of t. What do? I write f of t as f of t minus expectation of f hat L, the lower bound, plus minus plus. I just do this very simple thing. This is the bias, which I can ignore because it's always greater than or equal to 0. This is the random fluctuation, which can be bounded because this is finite. So of course this term exceeds this quantity for that particular h and for that particular bandwidth. And so I can have a bound like this for every value of h, for every value of t. Similarly, I can get an upper bound like this, okay, where now this test statistic comes up here. And I know that these two test statistics are finite, so I can look at the distribution of the maximum where I take these two kernels, and I can find now the quantile of this distribution t star, which is going to be finite. And I can say that I have a lower bound where I replace the statistic by its quantile. And that's really the simple procedure. And if you, so you get an L hat and U hat by just looking at this. Now remember that this is, I got this for every value of h. I can now choose my h. So I have lower bounds for every h, I choose the best lower bound. I have an upper bound, I choose the best upper bound. And then this leads to a confidence band for all f, which holds finite sample for all f in the class. There is no asymptotics going on here. Okay. So now let's show some figures. This is a linear function. This is of course a monotone function, and this is in a 50 square grid, and these are the bands that you get. Here it's a function just x1 greater than or equal to 0.5. It does not depend on the second variable, and it's piecewise constant. And as you can see, of course, these bands behave badly at the boundary, as you can see, because it's difficult to estimate, to get a right order on the bias at these points. But in the interior, you can see they're pretty good in the interior. And here, as you can see, that the width is very different from the width here, and these will be seen in the results. This is for convex. For convex, it is known that it's easier to get an upper bound, and the lower bound does not perform as well. And here is an illustration of what are the finite sample coverage probabilities of nominal 95% confidence intervals. And of course, for 0, which is a constant, or for an affine, we are guaranteed to have 0.95, the exact nominal percent. For others, it's slightly conservative. This is conservative because I want to ensure that I have a confidence band which holds for every value of f. There is no asymptotics going on. And so this is just an illustration. Now let's talk about optimality. Okay, so the first optimality result says that the rate of convergence of this confidence band is adaptive to the unknown beta. So now what do I mean by rate of convergence? So I now have a confidence band. So to take any confidence band, let us look at the supremum difference between the upper and the lower bound in a set an, where an is some set which is a subset of 0, 1 to the power d. And if that can be bounded by a constant delta that does not depend on n times something that depends on n, which is the rate, then we say the rate of convergence of this confidence band is gamma n on the set an. Okay? And of course, it's kind of known that without shape constraints or some qualitative assumptions, you cannot have confidence bands that hold for all functions in this function class. So the first result says I'm looking at monotone isotonic functions intersected with the Holder ball, sorry, not the Holder ball, the Holder class, where of course L is unknown, beta is of course unknown. Then I can get a confidence interval. My confidence bands have a rate of convergence which is optimal, which is log n over n to the power beta over 2 beta plus d. Okay. So here I'm saying that it's just only rate optimal. Okay. And of course you to do this I do not need to know what beta is. So you don't need to know beta and L. You get the optimal rate of convergence for estimating isotonic functions where the smoothness beta is between 0 to 1, and for convex functions where the smoothness is between 1 and 2. So of course this confidence band adapts to the unknown beta, because if beta is close to 1, then so if beta is larger, it automatically gives you smaller length. Okay, and these rates are optimal, and that's the first type of adaptation. The second type of adaptation I'm going to show is that it adapts to the intrinsic dimension of the function. So what do I mean by this? Yes.
Can you just comment on the restriction of beta is less than 1?
Here?
Yeah. Why is that necessary?
So you see, so for isotonic functions, like even in one dimension, you can at max get n to the power 1/3. So if you increase beta to 2 or more, or even anything more than 1, you will always be stuck with. So then, see here.
And you're not using a shape constraint estimator. You're doing frequency smoothing. And if I can easily find a monotone isotonic function that has 10 derivatives. I mean, I understand if you take the least squares estimator, but you don't. You're doing just frequency statistics.
Right. So even in one dimension, if you just assume that if you have a monotone function intersected with a beta h beta l, you cannot go beyond n to the power 1/3. So it's not only about using the LSE. You cannot improve it unless there are special situations where things vanish exactly to be 0 or something.
So if I would take now a class of monotone functions that have, say, bounded second derivatives.
Right.
And I would say no that even,
yeah.
Avoid maybe, but I don't see intrinsically why in your construction I cannot be adaptive. I understand this when you take the least squares estimator over the set of all like isotonic functions that you cannot get a better rate of convergence, but in this construction I don't fundamentally see why it should not work.
Yeah, I see your point. As of now, of course, the proofs, we cannot extend this beyond beta, beyond 1. But if you assume that the function is, say, beta equal to 10 and it's monotone, I'm not sure if you can get better than 1 over 2 plus d. I don't know. But that's a good question. I see your point. Okay. So now there's an interesting adaptation property, which is the adaptation to the intrinsic dimension or the number of relevant variables of f. So as I said, f is d-dimensional, right? F is a d-dimensional function, but suppose it depends only on k coordinates, i1 through ik. So it's really a k-dimensional function, but you do not know which coordinates, and so that is my class G1. So if you knew which coordinates, you would have just done isotonic regression with those relevant coordinates. But we can show that even if you do not know, the same procedure that you used can give you rates that now depend on k and not on d. So in that sense, they are adaptive to the intrinsic dimension and not the ambient dimension. Suppose if your isotonic function was an additive model, where there are d many one-dimensional functions, you get the rate of estimating a one-dimensional function. If you are in a situation where it's a function of many gi's, where each gi can only take a part of the relevant variables. So at max you have, say, xi1 to xil, and you have k many relevant variables in each of these functions. Even then, as soon as you if you restrict to the class with k being upper bounded by k, then you get a rate which is adaptive to k. And this is what I call as adaptation to the intrinsic dimension. Okay. So these are essentially k-dimensional functions, but you see them in a d-dimensional space, but these confidence bands adapt and give you k-dimensional rates. Not only that, suppose the function, so suppose now let's look at multivariate isotonic, and suppose if multivariate isotonic, there is a point where it's constant. So the function is constant in a neighborhood of, so this is the neighborhood. So I'm looking at the set of points where f is constant, and f is constant in a small neighborhood around t. Okay. So if the function is constant in a region, you might expect that the bands would be very, very tight. Indeed they are. You can show if that is the situation, my confidence bands, which use no knowledge of that, at especially those points where the function is constant, gives you a root n rate, which is what you would have done if you knew that the function is constant in that region. You would have probably just taken an average of the y's in that interval, and you would have gotten a root n rate. But this confidence bands adapt and give you n to the power minus 1/2.
Doesn't that even strengthen my question now? I mean, if you get this very fast rate in this case, you should get the optimal rate also for smoothness levels between 1 and very smooth.
Yeah, I see your point, but I don't know. I should say I don't know the answer. And even in one dimension, I don't know whether they have been shown beyond beta greater than 1. But I see your point. I see your point.
If you take a 3 times differentiable function, you can approximate it by, well, piecewise constant, maybe not so well, yes, but I mean, philosophically, I don't see the reason why you would rule out beta larger than 1. Okay. But okay, sure.
That's a good point. Thank you. So a similar thing would happen if you have a convex function, but that's affine in a region. If the function is affine in a particular space, you get exactly root n rate is the difference of the upper and lower limits in this confidence band. And my last slide, I'll end with some optimality results in terms of that our confidence band attains the minimum width locally. So now I'm going to assume something more. Suppose it's monotone, it's continuously differentiable, and every coordinate is relevant in the sense that the geometric mean of the derivatives of the function at that particular point x0 is greater than 0. Then the first impossibility result says that if you have any confidence band and if you look at an interval around this true point x0, then the difference of the function and the lower limit must exceed this quantity. So it's 1 minus epsilon times this quantity, and that's really the benchmark quantity I'm looking at. It must have this length, and we show L hat U hat constructed in this way essentially has that length plus an epsilon here. And but there is a bit of subtlety here. I am looking at just x0 here, whereas here I'm taking a soup over the interval. But this says that this constant factor is repeated exactly. So we are almost optimal in terms of length as well. And similar things could be done for U hat, the upper bound minus f. So yes.
The lower bound, what does f run over here? So this is a supremum over all f in.
So
fixed f? Or?
No, this is for fixed f, because these constants depend on this fixed f now.
But f is isotonic.
Yes, f is isotonic, and f I'm assuming something more if it's continuously differential.
What was the constant, or what was delta L?
Delta L is basically a universal constant that depends on the parameters of the problem.
But not on f.
No, it depends on f. Of course, it depends on f here too.
Is the result for some f or for
For all f. So if you fix an f,
You fix
this
it,
result.
It's not uniform.
No, it's not uniform. No, it's not uniform.
That would
See,
be- so
so this result was also not uniform.
Yeah.
Because here this delta L might depend on the function. Actually, no. So
For given f, the rate could potentially be much faster if it's a very smooth function. I'm assuming that you have just assuming it's continuously differentiable.
So essentially beta is like 1, slightly more than 1, and I'm assuming that the function varies in all its coordinates.
I mean, so let's say my f is isotonic infinitely differentiable. Does this lower bound apply to it or not?
No, of course not, because then this rate will not.
But how do I extract this from your theorem that it doesn't apply to it?
That's a good point. So okay. So you are saying that basically this is okay. So is there this? Okay. So let me think how it was framed. So we proved it for every fixed f. Let me think about this way. So yeah. How do we say?
We can take it offline.
Yeah. Okay. Okay. Take it offline. Okay. So now I want to end. Do I have 5 minutes? Okay. So I want to just end with a brief outline of the proof for the main result. So we showed that the multiscale statistic is finite, and to show that the multiscale statistic is finite, the main result we use is a result which is an extension of a result by Dungan and Spokane, which says if you have a stochastic process in a pseudometric with continuous sample paths, sub-Gaussian, for each a it's sub-Gaussian, sub-Gaussian increments, and then there's a very important result about the covering number of the space. And what we improve on is in the Dungan and Spokane paper, they do not have the log term, and we are saying if we have a log term, the same result holds. And if we have this additional log term, because as soon as you go beyond 1 dimension, you need a log term in the covering numbers, and with that extension we can prove the theorem for d dimensions. And another crucial aspect is that we are able to prove a tighter result in terms of the covering numbers, where we say that this was the v that came up. The v can still be 1, but we can have an additional log term in the in our covering number result. So I won't bore you with the details anymore. So this is just a summary of the ongoing work. And as I said, so we proposed a multiscale statistic. We used it to construct confidence bands and devise optimal tests into procedures. And of course, there are future directions. We haven't explored computationally feasible estimators, but I think the work of Walter and Monk and others have already showed that you can extend them beyond d equal to 1. And then we are able to detect only rectangles. You can think about more general shape regions, which you are yet to explore. Thank you. Thank you very much.
We have time for a question or two or three.
Yes.
You showed us some pictures of the bands. Do you have a comparison of pictures of like standard confidence bands which like use asymptotics without these constraints?
That's a good question. No, I don't have them here.
Can
But
you describe what happens?
no,
Like
we haven't done any simulation work on that.
I think it would be interesting to compare to see if your bands.
So one thing is that we are enforcing that it has to have guaranteed coverage, and the usual confidence bands that are usually drawn, they don't have guaranteed coverage for all functions in the function class, as far as my understanding goes.
Yeah, but it would still be interesting to see the.
Yes, absolutely, I completely agree with that. Yeah. So maybe in the paper we can have some of those plots. Yes. Yes. Yes.
So, I mean, maybe sort of a general question about this shape constraint literature. I mean, so there's all this energy and skill that goes into proving these very elaborate convergence rate results for least squares and shape constraint maximum likelihood estimators. But then if you actually want to make inference or confidence sets, one cannot really use them, it seems, and you have to go through more sort of classical frequentist constructions, or is this right?
So I don't completely agree with that, because in 1 dimension it has been shown you can do inference, because we can explicitly study the distribution theory of the MLE or the least squares
But you
estimate.
can't estimate the constants in the limit distribution consistently there. That's not true.
Yes.
And actually, your work on
Yeah.
inconsistency of the bootstrap has to do with this. So
Yes,
I don't
yes.
agree with this.
Yes. Agreed. I agree with you that
use
that it's
likelihood ratio things instead, though, right?
sorry.
Use likelihood ratio things instead, and then you get a universal limit.
So likelihood ratio is a way, but that's again that has guaranteed asymptotic coverage, not finite sample coverage.
But, so, I mean, what, I just computed like a ratio test under the set of isotonic.
Yes, and so this is the
what
work
is the
of.
diameter of this confidence set? Is it optimal or is it adaptive?
Okay, so they all assume that f prime at the particular point is non-zero. Okay, so it's not adaptive to this sort, means you can't have a piecewise constant, and then the rate will not change. So the rate is always n to the power minus 1/3. But you can get a tuning parameter free method that does inference that is asymptotically valid, but not valid for finite sample
Not
sizes.
adaptive.
Yes. Now you can ask how to do it beyond one dimension. I guess I don't know. I don't think anybody knows about that. So that's of course an important problem, I believe. But for the time being, if you cannot prove this, this is one way of doing it. Yeah. Thanks. Yes.
So maybe just simple question. So do you think by switching to some higher order polynomial you can fix this boundary problem? I mean, sort of like with classic convergence rates.
So to me, the problem is that as I said, the ultimate thing is that you have to be able to bound the bias, right? And as you go toward the boundary, there is really no good bound on the bias. So for example, you have an isotonic function. At the end point, it can really be anything, right? So I guess, yes, these shape constraint estimators have this problem that estimation of the boundary is very tricky. And in fact, the MLE is not even consistent at the boundary, at least in the regression setting. So now, is there a way to fix this? Yes, if you want to assume more. For example, you want to assume that the function has a particular variation or behaves in some sense close to the boundary. If you're willing to make those assumptions, you can incorporate those and get procedures which will be consistent at the boundary too. But here I have not used those things. Yeah. Any more questions?
I'm going to ask you about, in your setting, you always seem to have a Gaussian noise.
Yes.
What about if it's, and Brownian motion in
Yeah.
particular, what happens if it's something different, where you have dependence and
Yeah.
elements and that
So
thing, is the centering going to be a little different? Or?
yes, absolutely. So of course, so in my multiscale statistic, right? Yes. So this is assuming sub-Gaussian tails. If you have sub-exponential tails, maybe the square root would not be there. But yeah, I don't know. In general, I don't know if there is a way of finding this multiscale statistic that. Yeah. So every problem has to be geared. I think Axel has done some work with sub-exponentials, right? Where this penalization term is somewhat different. Yeah.
Depends on the tails you use.
Yeah. Yeah. Yeah.
Any more questions? If not, join me in thanking Bodhi for an interesting talk.